On June 24th at 1:24 a.m., the Champlain Towers South, located on 8777 Collins Avenue in the town of Surfside, Florida, collapsed suddenly, killing approximately 97 people so far. There were no unusual activities going at or around the building site that could explain the reason behind this collapse. The 12 stories of the building just pancaked on top of each other within a matter of 12 seconds. What we are going to look at today is some of the models of the pool deck that actually gave away first, and overall layout and locations of the columns that were present in the building, and how it actually contributed to the global collapse of this particular structure. Hi, I am Jinal Doshi, and welcome to Structural Madness. I am a licensed structural engineer in the state of Washington. I'm going to talk today about the possible reasons that could have led to this collapse of the building, and we will be reviewing the drawings as well as the collapsed pictures of the towers together and try and understand why and how could this catastrophic event have happened so that we can wrap our heads around it and figure out what can we do next so that we can prevent these kind of collapses in future. So in this particular talk, we are going to answer three different questions. How did the building collapse? We will look at the footage. What caused this collapse? So we will review the sequence of the collapse in this particular aspect. And then why did the building collapse? Like that's where we will answer or we will find the answers to our questions by reviewing some of the structural drawings, as well as we will look at some of the models that I have created to get a better understanding of some of the drawbacks that were present in terms of the detailing of the structure. So let us first look at how it collapsed. So we will review the collapse sequence of the Champlain Tower South. From multiple sources, the testimonies of the survivors, as well as people who have captured videos across the street of this building, it was quite evident that it was the pool deck that gave away first, and soon after, within a few minutes, the entire 12 stories of the Champlain Towers collapsed. This is one of the snippet of the widely circulated video that shows the garage and what was happening actually at that particular instance in the building. This is kind of showing that there was debris behind certain or a couple of columns in the garage. There was water that was flowing and kind of flooding the garage as well. So what I've identified over here is the three structural elements that we can see at the moment. So this is one of the structural walls. That's the northeast corner shear wall. There is one column right next to it, which is about 15 to 20 feet away from that, and then another column that's about another 20 feet away. So to get a better perspective on where that person was present while she was actually shooting this video, she was present right in front of the parking garage entrance. And if you understand this camera angle, then you can see that this is what was marked as the wall in the previous footage. So that's our wall right there. And this is column 1 and column 2. So you can see that's column 1 and column 2. These two columns are standing, so there was no collapse up until this location. And this is the actual shadow of the tower above. So it is quite evident that when this particular video was shot, there was potentially no collapse right along this column line. But all the debris that we are seeing are actually present from beyond that particular column too. That tells me that there was something going on over here which has led to the collapse of this particular zone of the pool deck slab. So that caught my interest. And now what we'll first understand is once the pool deck collapsed and after a few minutes, how did the tower collapse? You all have seen this video. It was like the front face of the tower first gave away, followed by the back facade of the tower. And then after 5 to 7 seconds, the northeast portion of the tower later on collapsed. So what do we understand from this? It is quite evident that first there was a local failure based on survivors' descriptions. It was like the pool deck gave away first, then after that the entire structure gave away. So why did the pool deck give away? Based on my initial observations of the pictures as well as the structural drawings, and looking at the Morabito's consultant's report back in 2018, um, it was quite evident that there was lots of corrosion, which leads to loss of structural strength of the system. There was lack of drainage as well because there was nothing like slope to drain that prevents water puddling. And then there was significant concrete damage because as soon as the rebars rust, it actually tries and spalls the concrete off because the rebar tries to expand as it's oxidized. And on top of it, there is some changes in chemical properties of the concrete as well. And as soon as concrete cracks, it becomes weaker and weaker, right? Um, and on top of it, what I also noticed is there were few locations on this pool deck where there was just inherent deficiency in the original structural design and the assumptions thereof. So these were the factors that I think did contribute. The factors that did not contribute were it was nothing like pool deck columns failed. The columns did have plenty of capacity. There was no evidence of seepage of seawater into the basement, or there was no significant differential settlement between the columns. And this aspect of differential settlement is reported by Morabito Associates in its unverified field survey report. So it doesn't seem like that had any role to play in this. So let's first look at what happened. Why did the collapse of the pool deck led to the building failure? The only common key between the collapse of the pool deck and the building failure are the columns that are actually circled over here, columns 1, 2, 3, and 4. These were the common elements that were common between the collapsed portion of the pool deck right there, as well as the columns that were supporting the tower. Apart from this, I couldn't find any link that was relating the two. Why did our pool deck collapse? So this is where we will start answering all the whys, like why did this happen? Why did the pool deck give away in the middle of the night? So as discussed previously, there were few reasons why the pool deck collapsed. One of the major reasons is definitely the rebar corrosion. And then there were also significant cracking. So as soon as I see significant cracking just under serviceable stages, that means your day-to-day building loads, which is like your floor slabs, weight itself without any additional load on it. For example, there's no one on the deck. There are no people. There is no car. There's nothing on the deck. It's just the deck that's supporting its own weight, along with the tiling and everything that's present, and the mechanical plumbing and everything that's present under side of the slab. Um, and just under those conditions, if a structural engineer sees significant cracking, then we start to question like, was there enough rebar to begin with in this particular slab design or not? And that's what I wanted to figure out. And to get to that point, I first looked at one of the video of the garage that was shot in July 2020. So that was like a year prior to today. So you can see that the ceiling of this particular pool deck is actually showing lots and lots of signs of cracking and water damage. Water was seeping literally everywhere underside of this deck. And when you see this kind of actions happening in a building, you know that there were two major issues. One of the issue was like there were no drains to kind of drain out the water that was accumulating on the floor above. And secondly, having that water seeping through your slab and spilling underside of the slab onto the basement floor below. That tells me that concrete cracks were kind of significant that allowed the water to seep through its cross section and drop down into the slab below. And this is where this is the portion that's most interesting for me, because it's right in front of this particular garage entrance, and it's our second column right there. If I just go back a bit, um, so that's our second column right there that was just visible in the video. And beyond this column, everything was kind of just rubble. So we know something happened right there. And what I'm showing over here is a shot by shot footage of the person's perspective and where they were in terms of the entire building footprint, like the basement footprint. So as you can see, when you're looking at uh, in this direction, you're looking towards parking stall number 52 and 54. So this is your 54 and 52 parking stall, and this is the perspective of the person. This is the camera angle. And then the person goes, circles around, and then moves into this direction. I've just cut some clips in between because I didn't find them overly useful at the moment. But in this clips as well, you can see that there is some sort of corrosion, or I shouldn't say corrosion, but there is some sort of water damage right there in this region, right? Um, and then if we move forward to the next slide, you see that there are some plastic corrugated sheets which are trying to divert the water from the cars below, which means that they were trying to reduce or kind of eliminate the damage that the cars will face when the salty water will fall on it. So that's why they did provide this corrugated plastic sheets. And this is what's very interesting. This is our column number 2 that we initially marked on plan, which actually survived. And this particular portion was collapsed in the garage video that was shot by the person right across the street. And what's interesting is this entire portion has been damaged by a lot of water seepage, while this portion is perfectly fine. Like, you can see how smooth this is, but this is all damaged. And what's surprising is right above this section, there is a planter wall, and you have soil fill and grass or trees or whatever they were growing at that time. That's all there. And you know that typically these soils are saturated. And if the soil is saturated, it will have water in it. And when the slab has some sort of minor cracking or significant cracking, that water is going to seep through the slab, and you will see its effects on the ceiling of the floor below. Correct? So keep this particular portion in mind. And also mind you that this soil fill was about 18 inches deep per the original architect's drawing. So it's also heavy. It's not like a very light soil. Since it's saturated, it actually adds to the weight. So again, going back to this, what does all this water penetration conveys to a structural engineer? And just to answer that, it seems like the serviceability level, the level at which the pool deck was designed and reinforced, it just seems little insufficient. And when I say this, I don't mean that it's going to collapse immediately as soon as the loads are imposed on a concrete structure. No, concrete is great at redistributing loads. It's great at kind of deform a bit and transfer the loads in some other fashion. So that's why you didn't see this collapse like in the past 40 years approximately. And it just happened overnight. And when it happens overnight, that kind of tells me that it was a brittle collapse, not a ductile collapse. And I'll get to that point later on in a few minutes over here. So the water penetration did damage a lot of steel and concrete in the slab for sure. I mean, you just don't usually see this kind of damage in basements. It's very rare, specifically for practicing engineers like me that are living on West Coast. And then when this water penetration becomes significant, it kind of damages the concrete as it passes along the cracks of the concrete. And along with this, what it also does is it leads to rebar corrosion. And when if you ever pay attention to a corroded iron or steel, you will see that a portion of the steel actually fall off. So what that also tells you is the area of cross section of the steel reinforcement has also reduced, which actually weakens the steel further. It damages the concrete around it because it oxidizes everything around it. And when the rebar actually corrodes, it tries to expand a bit, which leads to some additional cracking in the concrete. So we should also understand how did I came to this conclusion. So as typically structural engineers design buildings for two different conditions. One is your short burst sprint, that's the ultimate strength that the structure should have. That's your Usain Bolt condition. And the other is your marathon runner, serviceability, daily loads, your slab, that's your floor slab, your furniture, you without any guests in your house or apartments. These are the serviceability conditions, and that's your Eliud Kipchoge condition, right? And if I compare these two different conditions, one is like you have a large pool party, hundreds of people gathering on top of the pool. We don't want the pool to fail, right? And or else like the structure or the pool deck will be useless if you can't have a party. And the other condition is your Kipchoge condition, where you don't have a lot of people, but the structure sees some daily loads. And what that daily loads does is it actually creates long-term stresses on the system. And along with those long-term stresses, there is something called creep of the cross section, and with the creep you get some deflections, and with deflections you also get some minor concrete cracking. So we need to design for two entirely different conditions, and we have to satisfy different level of performance under these two conditions. So if I look at the ultimate strength condition, that's when the building experiences high stresses. That's the maximum possible load that we think the building is potentially going to see. And concrete does crack a little bit more under these conditions. The floors may deflect a little bit additionally, but they will be still within acceptable limits. And since these kind of conditions, like having a big pool party, doesn't happen every single day, 24 by 7, so we take some calculated risks and design the building efficiently, ingeniously, so that it is also cost efficient. Um, and then when you look at this serviceable conditions, then this is where it's like loads are experienced by the building on daily basis. And what we would like to see is we would like to have the building experience a lot less stresses and a lot less deflections under these conditions, as the loads are permanent. And these kind of loadings, as I mentioned, are your daily loadings, and it includes the structure's self-weight and some additional weight that you as an occupant are going to impose on the structural system. Um, and then when we design the building, the magnitude or quantity of steel that we provide, a lot of times is governed by this extreme loading condition. Um, and what this ensures is that the structure doesn't collapse when these kind of loading conditions do occur. Um, and under the serviceable limits, we don't want a lot of concrete cracking or water penetration issues, because we want to ensure occupant comfort. And occupant comfort only arrives when you have lower maintenance towards the building, right? And to ensure those lower magnitude of cracking, we also need to ensure that these sections or the structural elements themselves see lower stresses. So what was happening on Champlain Towers? It was as if like our desired performance was for the pool deck specifically, like it should have low stress, less deflection, less cracking, less water penetration issue, less demands on the structural steel, and this holistically ensures your occupant comfort. But what was actually happening? It was like the structure was under a lot of stress under these everyday loads everywhere. There were some significant water penetration issue, which causes occupant discomfort, and this actually leads to constantly uh, 100% utilization of your structural steel that was present. And it was like demanding uh, a marathon run from Usain Bolt, right? Like that's impossible. Like no person can run that fast for that long. Same thing goes for structures. Like they cannot just take like maximum magnitude of loads based on their capacities like every day. You can't ask a baby to run a marathon, right? It's that simple. So how did I assume that it was under designed to some degree? Not everywhere, but there were few spot locations that were highlighted when I was looking through the structural drawings. So what I did is I kind of created a pool deck slab model with the grade of concrete as 4000 psi that's been specified on structural drawings, as well as I did look at the member depths, that's 9.5 inch deck right there. And I applied all the superimposed loads. What are superimposed loads? So for example, you had like about 4 inches of extra kind of concrete material, which is like your additional waterproofing. You have some additional built up concrete on it. And then you also have your tiling over here, which is either made of clay or some other material, which is also significantly heavy. So once I applied just those superimposed loads, and I also applied a very minor magnitude of live load that's like 10 pounds a square feet. Typically, we design apartments for like what 40 pounds a square feet, and places or spots like pool deck are designed for like 100 pounds a square feet of live load. That means that many people are gonna be there. Like the density, the crowd is gonna be just huge. But in this particular condition, I just use like 10 psf of like live load on top, which kind of accounts for some accidental stresses, which are hard to understand just by looking at the drawings and even the survey reports. So based on the floor slab model, um, what I what I found out was there were few elements in the pool deck that were kind of uh, looking for like Usain Bolt performance. The ultimate strength level demands were imposed onto these elements, even though I haven't used any load factors. So what are load factors? So if I say that there will be 100 psf of live load, that means there will be a person every 2 or so square feet. um, we amplify those loads by another factor to account for some uncertainties in terms of member capacities and the actual loading conditions. So there were no load factors that were used like that to increase the demands onto these elements. And then too, the beams that are present underneath here, they were highly stressed. And on top of it, I also noticed that there was punching shear issue around these columns because of these heavier soil loading as well, which kind of tells me that the structure itself was like it was seeing very high stresses, even though there were hardly anyone on the pool deck. So this was my slab model that I kind of just quickly create to kind of get a rough idea of what the stresses were. And again, as you see, like my demands are very close to the design capacities. These are not the actual expected capacities, but we call these as design capacities, which are a little bit lower than actual expected capacities. And on top of this, I did notice the beams that are highlighted in red were also kind of overstressed, and the rebar that in I should say structural steel that was provided was also just barely enough to handle these serviceable conditions. That's your day-to-day loading condition. Um, and then this particular image actually caught my eye. What was interesting is I saw like there were just two reinforcement that was two rebar. That's two number 5 reinforcement that was coming out of the column, which is kind of a bit unusual because typically there should be 4 or 5 reinforcement per the structural drawings that should be going through the column. And when you have very low reinforcement at the slab column joint, what happens is your capacity of your slab's punching shear actually reduces, and it reduces far below what the code specifies as your building punching shear capacity limit. So, for example, this is my 1.0 is my demand to capacity ratio. This is the actual capacity of the section under any particular load. Like the capacity is just based on geometry. It has nothing to do with the loading conditions. And demands actually come from loading. And loading is what? Your self weight of the slab, your additional tiling, your mechanical stuff, your furniture, and et cetera, et cetera, et cetera. And we reduce that capacity by a factor, and we call it like a material safety factor, which accounts for some material uncertainties. And even after that reduction, um, when you have this low reinforcement ratio, and when you also have this impacts of corrosion because of concrete cracking and water damages, your capacity keeps going further and further down. And this is a big concern now because since the building was built in 1980s, there was no punching shear reinforcement that can handle additional punching shear stresses. So whenever, if and ever a time comes that your last aggregate interlock or your last line of defense kind of gives away, it'll be like a sudden collapse of this pool deck. This is what punching shear kind of looks like, is your top reinforcement kind of goes over the column, and there are some minor cracking which are kind of expected because concrete cannot take tension, right? It cannot take this your pulling force. That's why we provide steel, or else we wouldn't provide steel. And based on the magnitude of steel, the percentage of steel, or the number of bars that you are providing, the lesser the number of bars, the wider your cracks will be. And the wider your cracks will be, the lower your punching resistance will be. Because for punching resistance, it is essential to have less cracking so that aggregate interlock of concrete holds in place and resist your punching shear forces. But when this rebar reduces, your crack actually widens up significantly, causing lower capacity of punching shear. So this is how a material could potentially degrade with significant magnitude of damages. But it was not just the degradation of material, as we found out. It was also the section was kind of under designed, like just under your serviceable loads, just under the self weight of the materials. It was like the demand to capacity ratio of this section was like almost close to 1.0. So that's what this degraded line is showing. And what it's showing is typically people expect, looking by drawings, like, oh, this is what my expected line should be. So my structure should be good, right? But no, that's not what it is. Your members itself were a bit under designed, and that will lead to a premature failure than what anyone would expect. That's the key here. And on top of it, maybe this is just a mistake they may have caught while constructing the building, but there were no top reinforcement in between the columns like you usually see on the drawings. There was just no reinforcement called out. So that's a little bit surprising to me. But if this were the issue, then we would have seen some additional damages prior to this. So I am kind of questioning that. I may be wrong over there, and that's why I've put a question mark, like may or may not be provided top reinforcement right there. And then on top of it, another area that caught my attention was a few columns right here, right next to the pool deck. And why was that interesting for me? It was mainly interesting because the slab span over here is like 30 feet. Ask any structural engineer today, what should be the slab thickness for a 30-foot span when you have a heavier loading like pool deck? And I can confidently say that their answer will be like 12 inches thick slab if it's a mild slab, if there is no post tensioning in it. And that's why it was like, why do they have like a 9.5 inch thick slab? Because that would lead to some deflection issues. That would also tell me that there will be more punching shear issues over here because the loading is more on each column as your slab is trying to span more, right? And that's exactly what happened. Is when I actually ran the analysis model, what I saw was there was this large band of higher concrete deflection just under your dead load and your material load. This is not even including any sort of live load, right? So this tells me that the structure was deflecting a whole lot. And again, that's why you have those water penetration issues everywhere under garage, right? On the under the underside of the pool deck slab. And on top of it, Typically, when you have this large span on a pool deck slab, we would expect a little bit higher reinforcement, and that's exactly what the software gave me. It's like the reinforcement that was provided was like barely enough to handle or support its own weight. Again, the slab is not going to collapse immediately. This is like your tension reinforcement. So what happens is, as soon as the structure sees a little bit higher loads, your rebar kind of stretches like, not exactly like a rubber band, but you can exaggerate it like that. So it stretches itself like a rubber band, and your crack width kind of increases. So your crack opens up and you have more water penetration issues. You have a little bit additional deflection on top of it, right? But it's not going to feel like immediately. But this was also a severe concern in my mind. And this also showed like, hey, there will be punch and shear issues, and that was the case. Like, and I do expect like 33% additional steel in such longer span, but there was no additional bottom steel that was called out on plan. Even the top steel was kind of barely enough to handle again its own weight. So I don't know if there was a design change later on in the project that led to this issue. And now when you think about like how there were just two rebar that were going through the column, if you kind of apply something similar over here, then yeah, I mean, it's like no surprises over here. Like the pool deck could have collapsed earlier or later, depending on what was the magnitude of damage that was done by water penetration. And was punching shear the only problem? I would say no, because just like I showed you, there were some flexural reinforcement that additional flexural reinforcement was required than what was provided. So as soon as you have lower flexural reinforcement, your slab deflects more. But as concrete reinforced with steel is really good in terms of redistributing its loads. So that's what could have happened is concrete was redistributing the loads, but then it was also under a lot of stress constantly every day. It was just like waiting to collapse as soon as your last failure mechanisms or mechanism to resist these loads kind of gave away. Um, so this is your concrete. You can imagine it kind of as kind of a tug of war. Like if one of the person in your team is not like pulling efficiently, everyone else are still going to try hard. But then because one of the person is not working hard enough, suddenly after some time you will be fatigued and you may just give away. You're like, I cannot take it anymore. The other team on the opposite side is giving its 100% while I'm just giving my 75% on my team, right? So that potentially does happen over here. So what was the scale of this pool that collapsed prior to the building collapse? I personally think that it was not just the highlighted red section that we were discussing before that collapsed. What I do think, based on the analysis, is this entire section did collapse first. It was not just that local failure. And why do I confidently say that? Is again, low punching shear capacity. And you can see the columns have punched right through the slab. It's like punching through the paper with your pen, right? And there is no additional debris over here. So it's not like these structures, debris actually caused this additional collapse of the pool deck. No, there is no way. It's just your pool deck actually gave away first. And why did it kind of do this? If you notice, this particular pooled wall were kind of almost a story tall, so it had a lot of stiffness over here. And this column was also very close to the pool deck, along with the jacuzzi's walls over here. So this slab could not just shear off right there. It had a lot of shear capacity. So that's why it kind of did this jog and came over here and then collapsed right in this entire zone. And this was your first collapse in this entire collapse sequence. Like it's 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 fairly accurate to say that this could have happened. Now let's focus on what triggered the tower collapse. This was the collapse pool deck. This is a step beam, and this step beam was more or less detailed as a step rather than a beam. So there were some lack of reinforcement. If if the pool deck gave away. Your existing reinforcement in that step beam was not sufficient to kind of handle additional stresses. So this is what I'm showing. Like this is your collapsed pool deck, and what it does is it causes additional stresses onto these step beam elements, which were just 12 inches wide, and the detailing was not clear enough. Like, where is your top rebar over here? I'm 100% sure. I shouldn't say 100%, but I'm fairly sure that they would have hooked the bars like this because they're showing it on plan right there. A hooked top reinforcement, number 5 at 12 inches on center. So even if they have missed on detail, on plans, a contractor can catch it and provide it. It's fairly typical to miss few things here or there, but that's why during construction stages, contractor do ask us questions like, what's our intent over here? So this reinforcement must be there, but that's the reinforcement that's holding it and transferring loads to the beam over here. And again, this beam doesn't have a ton of reinforcing. It's just like two number 5 flimsy tops, and that's it. There's nothing else. And that kind of surprised me again because just uh, just based on the collapse section and how much weight it will impose onto this beam, it's like just by the dead load of the slab itself, I require like 3 or 5, 4 number 5s at the column support over here, while the drawings are calling out just 2 number 5s, and there is nowhere else that where they have specified any beam reinforcement. And on top of it, the shear demands on the beams also increase. So what I do think could have happened is after a few moments of the full pool deck collapse, this particular step beam could have given away. And as soon as it gives away, your columns actually are free. Like there is nothing that's kind of restraining the column from any sideway movement. Um, and also, it was kind of interesting. I'm not blaming that it was Jim. That's presented on architectural drawings from 1980s. That could have lead to some additional stresses. I'm not 100% sure, but I was just reviewing drawings, and this is what I was kind of finding out. And I haven't even accounted for this additional gym loading and its equipments and everything, which actually adds quite a bit. Um, and since that's not included, I can more or less kind of confidently say that without inclusion of this gym's additional load, the beam was already on the verge of failure. So if there were these additional loads present, then it could very well be that these beams would have failed first. And if we look at the video footage of the collapsed towers, these are the columns that actually gave away first. So that tells me that these columns failed soon after the pool deck collapsed and this particular beam collapsed. Um, why would the column fail? What's interesting is the columns that were present here were just 16 inches by 16 inches, supporting 12 stories. That is too skinny. When you are supporting 16 stories with a heavy pool deck, I would expect a 20 by 20 or 24 by 24 columns on the perimeter, specifically on the perimeter because they are prone, like they are on the exterior portion of the slab and they are more prone to weathering effects. And because they are not on the center, they also see some additional stresses because of your punching shear and unbalanced moments coming from the slab into the column. So what could have happened is as soon as the beam and the slab gave away, there must be some sort of necking that must have formed around those columns right there because your slab is going to pull out some concrete around it. And when that happens, your column's cross-sectional area reduces further. And there is something called column buckling. If you remember Charlie Chaplin as the character and his stick, you would see this kind of buckled shape. Now, the stick doesn't break because it's very ductile. It's like taking your steel reinforcement and stretching it out further and further. Steel can stretch, but concrete cannot. Concrete is very, very brittle. So, as soon as it sees some sort of deformations like this, it could potentially give away, specifically with some sort of necking that was happening right at the L1 pool deck and the column interface. I'm not 100% sure about this, but this could be one of the potential reasons behind the failure of the columns. So if a couple of columns fail, then why did the entire building fail? So if I take these three columns out, what happens is the slab kind of tries to hang uh, with the support of the neighboring or surrounding steel, and then you have columns around it, right? And then these columns are supporting the slabs over here. But then what was interesting is the top 3 or 4 stories of this particular building had lower strength concrete for the floor slab. For pool deck, for example, it was 4,000 psi, but on the roof on level 8 and above, it was just 3,000 psi, which means it has 14% lower punching shear capacity. And on top of it, what these columns will see is they will face some additional stresses because now this particular highlighted portion of the slab is trying to hang off of the other sections of the slab. And as soon as these stresses increases with a little bit lower punching shear capacity, that's when these columns give away. And this way, your collapse is kind of triggering further and further into the building footprint. But then what's interesting is you have a giant shear wall over here and here. And these shear walls are designed for like a significant amount of wind and seismic loads. If the building is on West Coast, then they will be designed for seismic loads. But since this was in Florida, they'll be designed for like a very high category typhoons, right? So that's where these shear walls they won't easily give away. They won't be uh, collapsing just because of some thrust that's being imposed by these accidental slab that's collapsing at this instant. So that's why the slab just literally sheared off right there, and this entire building was saved, and the collapse didn't even progress further. Something similar happened over here momentarily. This entire section gave away. This portion of the building actually stood up for 7 to 8 seconds, I think. And then what you would notice is you have shear walls in this particular direction. That's your page left, right. There is no shear wall over there in page left, right direction. So slowly, because of some instabilities and damages in floors below, the columns as well as this 12-inch thick wall just literally gave away because yeah, it didn't have enough stability in that direction. So you can see that it's standing and then it actually caved in this way. And when you look at from the top, that portion never did come down. It actually went towards the inside of the building. So it was, this is its footprint right there, right? So if I take the top line right there, it actually caved in this way. That's why you see these steps over here. And why am I confident that it was the punching failure of the slab? Look at all these columns. They are like straight chains and literally kind of no damage, right? So that just quickly tells me that the slabs were like punch, 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 and then columns were just kind of going down wonk like that because there's no slab supporting the column anymore. So to summarize this entire discussion, it was like the pool deck started this collapse chain. It's quite obvious. And the pool deck did collapse because of less quantity of steel than required. There was lesser thickness of slab than what we would typically expect. Then there was lack of proper slope to drains so that you can drain the water and prevent any damages on concrete. There was also lack of maintenance in this case. There was also less than desired concrete cover. It was just 3/4 inch concrete cover in these extreme environments, while I would say we need somewhere between an inch or inch and a quarter cover in such locations. Then there was also lack of structural integrity reinforcement, which was introduced in later provisions of the code. I would say somewhere around 1990s. So this building was built prior to that. And then less than desired quantity of reinforcement between slab and column connection. That was evident from after collapse pictures. So that must have happened during construction. Um, with this, I would like to conclude my discussion today. I hope this helped you in getting some insights behind the collapse of Champlain Towers. Again, these are just my initial observations. Um, it could very well be the site conditions or the reinforcing at the site during construction may have changed or added based on some of the findings later on. I'm unsure, and we will just find it out when NIST actually concludes their investigation. But so far, as a structural engineer, I do see these as major concerns that could have contributed to the collapse of Champlain Towers. Thank you, and I will see you next time in completely separate discussions. Take care.